Hi guys, thank you so much for coming to this lesson. So today we're going to be covering a proof, but the A-level side of it. So if you haven't already, make sure you fully understood the A-level proof that we covered earlier. But today the learning objectives is to be able to understand and use proof by contradiction, and with specific applications to the irrationality of the square root of 2 and the infinity of prime. So if you haven't, so like always, there's going to be timestamps in the description. So feel free to skip to parts you want to cover or go back, whatever. Okay, so firstly, what is proof by contradiction? So proof by contradiction is when you have a statement or your conjecture, what you're trying to prove. So in this case, we have that prove that root 2 is irrational. And what you have to do is you have to assume that the opposite is true. So in this case, you'd assume that root 2 is actually rational, and using that, you'd follow steps, and then you'll reach a conclusion saying, oh, using this opposite assumption, this doesn't make sense. So therefore, by contradiction, the statement is actually true. So it'll make more sense if we go through an example. So if we have proved that root 2 is irrational, as I said before, the first step is to say that root 2 is actually rational. So if you remember what a rational number is, that's like a fraction. So you could say that root 2 is equal to a over b, so that's a fraction, where a and b are integers, and this fraction, and the fraction is in the simplest form. This basically means that the a and b have no common factors. Because let's say a was 4 and b was 2, they could just cancel each other out and the whole fraction just become 2. So you got to make sure that you can't cancel out the fraction again for it to be a rational number. So so assuming that root 2 is equal to a over b, the first step would just be to square both sides. So you could just say 2 equals to a squared over b, and then if over b squared, and then if you rearrange this, you get 2b squared is equal to a squared. This therefore implies that a squared is even, as a squared is 2b squared. And this further implies that a has to be even, because if the square root is even, then the square number is even, the square root also has to be even. So then if we do the same, therefore we can call that a could be 2k. So then we could write that 2b squared is equal to 2k squared, which is just equal to 4k squared. So that means that b squared is therefore equal to 2k squared. And using what we said before, this means that b squared is even, which implies that b is also even. But this contradicts this bit that we had before, that the fraction is in the simplest form, because if they're both even, then that means they both have a common multiple of 2. So this basically, this therefore means that if a and b are both even, then a over b is not in the simplest form. So therefore, by contradiction, root 2 is irrational. Yeah, so to go over this step again, to go over what we just did, so we started with the assumption that, the opposite assumption that root 2 is actually rational, and then using all these steps, we came to the conclusion that if root 2 is rational, then the first assumption that we had here doesn't make sense. So then by contradiction, the root 2 is actually irrational. The next example we're going to go through is we're going to prove that there are infinitely many number of prime numbers. So to do this, similarly to before, you have to assume the opposite. So we're going to assume that there are a finite number of prime numbers. So assume finite number of prime numbers. So you could write them out as P1, P2, P3, all the way to Pn. And then, so let's say there's another number, P, and that's equal to the multiplication of all the prime numbers, P1, P2, P3, all the way to Pn, then you plus 1. So you could say that P could either be prime or not prime. So let's say P is prime, then that means it was not on our original list, and that immediately contradicts the fact that there are a finite number of prime numbers. So it's not on the list. But you could also say that, let's say P is not prime, and it's known that every number is a product of prime numbers. So if P is not prime, then that means that one of these, and if there are a finite number of prime numbers, then it means that one of these prime numbers have to be a factor of P. But if that is the case, then this bit, it could be a factor of this, it could be a factor of this bit, but you'd always have a plus 1 on the end. So these prime numbers are not fully divisible into P. So that means it's impossible for one of the prime numbers on our list to be a factor of this. So that means P can't be prime. So this is therefore, which is impossible. Therefore, this can't happen. So this is a contradiction. This is a contradiction of the first claim. So then this means that because this can't happen, if it's not on the list, then that's the immediate contradiction. And if it's impossible for P not to be prime, which means that it has to be prime, then therefore there is not a finite number of primes, and therefore by contradiction there's an infinitely many number of prime numbers. Infinite number of prime. So we've gone through two main examples of proof by contradiction, which you do need to learn, as they could easily ask you them. But they could also ask you to apply proof by contradiction in other examples. So using the method that we just did, where we assumed the opposite of the statement was false, and then we went through and showed that that was impossible, and so the original statement has to be true. Try this question, pause the video, try the question, and then come back to the solution. Okay, so question is, prove that there exist no integers a, b for which satisfies 5a plus 15b is equal to 1. So the first thing you need to do is assume the opposite is true. So assume that there does exist a and b. So then you have, so if you have 5a plus 15b equals 1, they exist integers, a, b. So if you have that equal to 1, then you could simplify this and cancel out 5. So you say, divide everything by 5. So you say a plus 3b is equal to 1 over 5. But if a and b are integers, so if a, b are integers, then this implies that a plus 3b also has to be an integer, because if you add together two whole numbers, you're going to end up with a whole number. But this contradicts the fact that a plus 3b is 1 over 5, which is not a whole number. Therefore, you get a contradiction. And so the original statement that there exists no integers a, b for which satisfies 5a plus 15b equals 1 is true. So thank you for coming to this lesson. So to just sum up, we learnt proof by contradiction and the applications to irrationality, a square root of 2, and the infinity of primes. So yeah, so this is the A-level side to proof, as I said before, but that we also learnt proof by deduction, exhaustion, and disproof by counterexample in the AS video. So go back to that for like the full understanding of proof. Yeah, so those were only two examples, but you could get asked any. So make sure you do some practice questions on this to make sure you fully understand. But yeah, thank you so much.